Okay, so we're going to find the directional derivative of f of x, y, z equals the square root of x squared plus y squared plus z squared at the point 1, negative 2, 2. So what does that mean? When you find a derivative at a point, you're going to get a number, right? And then it's in the direction of v equals negative 2, 3, negative 6. So the directional derivative d u f of x, y, z, u is, even though there's no arrow over it, that's the direction vector, the unit direction vector, right? So remembering that and remembering this notation tells you to do what? You got to find the unit vector. Here's a vector that's parallel to the unit vector, but unless the magnitude of it's 1, it's not the unit vector. So the first step would be to turn v into a unit vector. So what do? Take the magnitude. Okay, so what's the magnitude then? Square root of what? 4 plus 9 plus 36. 4 plus 9 plus 36. That's the square root of 49. 49. And that's 7. Yeah. So our u would be 1/7 times v, right? If we want to stick with component form, 1/7 on the outside we could write, and then negative 2, 3, negative 6. Okay? So this might be different than how you guys try it, but see if you like this method. So remember what the directional derivative is in terms of a dot product? Isn't it del f dotted with u? I, for some reason, like that way to remember it. I don't know why, I just do. So I'm going to do it according to that formula. In other words, I'm going to find del f. I already have u. I'm going to find del f, and I'm going to take the dot product. Now, I'm going to find del f evaluated at 1, negative 2, 2 first, though, right? And then take the dot product, and I'm done. So, okay, I'm going to need this, circle this. And then, okay, del f, I need the partials. I'm only going to have to take one partial here, and I can figure out what the others are based on some symmetry that's going to happen with this nice function. So I'll write them all down, but I'll show you how to think about just in terms of one of these things. So you can think of this as x squared plus y squared. F is x squared plus y squared plus z squared to what power? 1/2 power. So take the derivative with respect to x. What do you get? 1/2 times that, yeah, x squared plus y squared plus z squared to the negative 1/2 times 2x, which is the same as what? X over the square root. Okay. So what's the only thing that's going to change in the other partials? The chain rule part of it, where instead of getting 2x, you'll get 2y for f sub y as a factor and 2z when you take f sub z, right? So the numerator is the only thing that's going to change, isn't it? So you don't have to think a whole lot about f sub y. It's going to be y over that square root, isn't it? And then f sub z will be z over that square root. Now, the denominator is the same for all of these, right? So a little time saver will be to figure out what that is when you plug in the values of x, y, and z. So one note you might want to make is the square root of, here's your x, your y, and your z. So you're going to take the square root of 1 squared, which is 1, plus 4, that's 2 squared, plus z is 4. Oh, that's nice number 2, isn't it? Square root of 9, 3. Okay, so then what do these partials become then when you plug in? Now, whenever you plug in something, you should indicate, you should use the full notation. So then f sub x evaluated at that point is going to be what? Well, it's going to be x, right? Which is 1 over whatever you get when you plug in 1, negative 2, 2 into the square root. Oh, it's 3 each time. The denominator is going to be the same each time, right? So it's, what, 3, oh, whoops, wrong one. 3 in the bottom, 1 over 3, right? And then what do you get for that guy? Negative 2 over 3, and for f sub z evaluated at the point, 2 over 3. So we're just putting this guy, that's the z value, right in there. And then we know the denominator is 3. So then that gives me del f evaluated at 1, negative 2, 2. And that is the vector 1/3, negative 2/3, and 2/3. Everybody with me? Okay, so then my directional derivative let's cut to the chase and just put in the correct inputs right away. 1 evaluated at 1, negative 2, 2 is going to be this vector, del f, dotted with this guy, right? Now, why didn't I multiply out that 1/7? You can leave it on the outside, take the dot product, and then you're going to have a constant times 1/7, right? So it would look like this. Might need a little bit more room. Go over here, and then we'll mark that off. So we're going to take del f, which is 1/3, negative 2/3, 2/3. We're going to dot it with 1/7, which you can just pull out as a scalar multiple out front, times negative 2, 3, negative 6. Going outside the video a little bit, so let me go over like that. Everybody believe that? Okay. And then we get I'll pull the 1/7 out front. Let's take the dot product. Okay, focus on the right things. This guy and this guy. This guy and this guy. This guy and this guy. You multiply corresponding components and add, right? Remember, the directional derivative is not a vector. It's a scalar quantity. And if you're given a specific point to plug in, it's a number, right? So little things like that can tell you if you made a mistake. If you get a vector when you're done, something's not right. And that happens all the time to Calc 3 students, because they just forget, right? But if you know what stuff is and you understand, and you have a certain level of understanding, it's not that you won't make mistakes. I make mistakes all the time. You're going to find those mistakes. You're going to have the ability to find those mistakes more easily if you understand what's going on and what these objects that you're playing with should look like. Okay, so I'll just put it in parentheses then. What do we get? Negative 2/3. And then what? Minus 6/3. I'll take a chance and go with minus 2. See if we get any nice cancellation. And then what about 2/3 times negative 6? Which would be negative 4. Okay. And then, I don't know why I switched to blue, but I did. 1/7. Okay, so then we get negative 2/3 minus 6, which is minus 18/3. Yeah? And then what does that create in here then? Minus 20/3 times the 1/7 out front still. And when you multiply those together, there you go. So that's the slope of the function at the point 1, negative 2, 2 in the direction of v or u, whichever one you want to look at.